Hello and welcome to everyone. We're Team SIO, and we're here today to talk to you about our gyroscopic-based hand stabilization device for Parkinson's disease and essential tremor. This is, my name's Alex. On the end there is Will, Alvin, Joe. This is Mike, Josh, and Victor. Now I'm going to pass it off to Mike to tell you about our problem statement.
Thank you. So essential tremor and Parkinson's disease are disorders that cause tremors throughout the body, and these tremors make it difficult for those suffering from these disorders to perform tasks which require precision movements, such as using a computer mouse or writing with a pen. Now currently there aren't any treatments for this that are permanent, and devices out there that exist are either too expensive, they're cumbersome, or they only allow the user to perform specific tasks. So this brings us to what can we do to help. So our goals for this design was to come up with a device that is convenient and inexpensive for the user to use for many different tasks, and to implement a monitoring system that allows the user to get feedback on whether or not the device is making the shaking worse or better, and being able to provide that data to a healthcare professional for further diagnosis and rehab. So to pass it off to our design process for this semester, I'll hand it off to Josh.
Thank you, Mike. Okay, in the beginning, for our project, we decided to attack it from two different ends. We wanted to work on the finger stabilization, and we also wanted to work on the hand shaking. For our first thing, we wanted to implement like a servo and pulley system to dampen the shaking of the fingers. We 3D printed a hand, an exoskeleton of a hand, and we strategically placed servos on the wrist, and as we pulled those lines tighter, it would take the hands and have the fingers stop shaking. Overall, we found out it was a little too complex, time consuming, and not cost efficient because of the servos, and we wanted to maybe implement it with our other design, and the wires kind of got in the way. So for our solution, we did a gyroscopic based glove. What we're doing is we're putting a gyroscope over the hand. We're spinning it up at 13,000 RPMs with a DC brushless motor, and using the gyroscopic force to dampen the shake from the Parkinson's disease. We implemented an accelerometer to track the acceleration of the hand, and we're choosing to stream it live to our GUI so we can see in live time what the accelerometer is doing, and we're able to keep that data in a data file. And we also, for convenience, we wanted to implement a voice control system to operate our device. To show our device and talk about this video, here is Victor.
Okay, well, what this is supposed to show is that basically, because we don't have a Parkinson's patient on call 24/7, what we do is that we use a muscle stimulus device to essentially mimic the tremors from Parkinson's. So what we do is that for testing, we hook up a person to the device, and so what we do is we stimulate the muscles at certain frequencies and intensities to mimic certain severities of Parkinson's disease. And so on the left, you can see that this is our test. This is with just stimulus device, no gyro spinning. While on the right, or on the left, is both the muscle stimulus device and the gyroscope spinning at the same time. So you can see there's a pretty big difference. So this is our overall glove design. So our glove has two parts. We have the hand unit, which houses the motor, the accelerometer, and the gyroscope. And we have the control unit, which holds the ESC, PCB, a TI chip, and the battery. And the control panel, our control unit, also features two LEDs and a control calibration button. And so one LED will indicate low battery, while another LED will indicate different prompts for calibration. And so what's supposed to show here is basically it's going to be a 3D render of our handheld unit. And basically you would see the gyroscope, motor, and accelerometer within it. So our gyroscope housing, which extends off the back of the hand, is roughly 2.5 inches in height. And the total weight of our handheld unit is about 204 grams. And so on the left you see our actual gyroscope. It's made of two parts. One part is the ABS housing, and it's 3.5 inches in diameter with a hollowed out insert. And what we do is that in that hollowed out space, we insert a steel ring, which for us is 85 grams. And what this does is that it brings the total weight of the gyroscope towards the outer edges. And what this does is that we bring down the overall total weight of the gyroscope while increasing the force. So you get more force out of the amount of weight we're putting in. And so we'll be spinning this at 13,000 RPM. And to give you this is an overview, Christian.
Thank you, Victor. Good morning, everyone. So this is the block diagram for our entire design. So on the top portion there would be the voice recognition portion of it, which would the ADC, the DS-PIC would pick up samples using the ADC from the microphone and get those samples and compare them against samples stored in the EEPROM. And then, according if there was a match or not, it would go ahead and send a PWM signal to the motor. In the middle portion in red, we can see the accelerometer talking to our DS-PIC using I2C. And then we get that data and then send it to our GUI using, after it's been created into packets using UART. And in the bottom portion, we can see it's our battery, which is connected using a mechanical switch, and it's powering both our DS-PIC, our PIC-12, which is used as a battery monitoring system, our ESC, and our motor. And then the next slide shows that that's a circuit board which represents a physical representation of our block diagram. And to talk more about voice recognition, here's Alex.
So the purpose for voice recognition was to provide a hands-free method of interacting with the glove. In order to do this, we chose a couple of words, as you can see on the board, to be recognized. And the way we went about doing this is by taking a shifting window Fourier transform of the speech. What does that mean? Well, it means we're looking at the frequency components of what has been said and how that changes over time. Currently, this is still in development in MATLAB. Due to our low sampling rate, we're getting a relatively poor signal-to-noise ratio compared to what we would need to perform a match. Whereas in MATLAB, with better quality data, you can get plots such as these. So here on the left, you can see a reference for a spoken sample of the word on, and on the right, you can see a separately taken spoken sample, again, of the word on. And as you can see here, the energy is developed along very distinct patterns here. Whereas if you compare this to a incorrect match, you can see that they don't look anything alike. This can then be taken and create plots like this, where you can take and plot the maximum frequency at each time interval and look at that and compare it to the reference sample. What we've done here is we've compressed an entire second's worth of data down to 10 points. We can then take this and shift it, because of how few points it is, viably shift it across the reference sample and look for a match. In doing so, we've made how loud you spoke unimportant, and we've made when you spoke unimportant. Additionally, we can provide a percentage match to frequency deviation in your voice based on just looking at the amplitude, which in this case represents the frequency. Next, you can see this is a plot of the incorrect match bat, and you can see they look very different, and no amount of shifting or percentage bias would help with this match. Next, to talk about the GUI, here's Alvin.
So when our DS-PIC starts, it will initialize our I2C, accelerometer, UART, and PWM components. Once that is done, the DS-PIC will wait until it receives a data byte from our GUI. Depending on that data byte, it will either set the speed of the motor or tell the DS-PIC to start sending it accelerometer data. To go into more detail about the accelerometer and the GUI, our accelerometer is set to output 14-bit data in 2G mode, and that data will be live streamed into our GUI, where it will graph the acceleration in real time. Our GUI can control the speed of the motor using 5 speeds, and it can also save the data being plotted into a text file for the user to read, and also features the ability to replay that data for future use. Now to talk more about our power system, here's Mike.
So to power our device, we chose to go with the 2-cell lithium polymer battery, which will provide 7.4 volts and 1,200 milliamp hours capacity, which means we'll have roughly 2 hours of runtime for this device before needing to be charged. The battery will then power the ESC and motor, and will also power the DS-PIC 33 through a voltage regulator, and also powers the PIC-12 through another voltage regulator. And the purpose of the PIC-12 is to monitor the battery voltage through ADC And when the battery voltage drops too low, we'll be able to cut off power through a solid state relay, which acts as a MOSFET switch, but is easier to implement than a MOSFET switch. And it also acts as a failsafe for the DSPIC33, so that it'll read a pulse on a pin from the DSPIC33, and if it receives a pulse, that means the DSPIC33 is operating as we want it to be, and if it should go through an extended amount of time without receiving a pulse, then something must have gone wrong, and we will again cut power through the solid state relay. And this failsafe also acts as an FDA requirement should we want to push this device into production and put it into the medical field and other such applications. To talk more about our budget, here's Will.
For the budget, the goal was to keep the entire product, one glove, under $100. For prototype testing, we needed to keep it under $750. Based on the block diagram, our product is going to be under $80, which is well below the $100 goal. As you can see here, most of the money was spent on the charger. So since time was a big concern, we needed something to stay on task and meet the deadlines. Milestones provided a timeline of what and when things should be working. As you can see here, these are key milestones. We needed to spin the motor with PWM, be able to communicate via I2C, have the first PCB printed, and have a fully functional glove by May 1st. Next is supposed to be a video of our riding test. Basically what this is the first one is a control test. Basically Josh with just writing his name out without the muscle stimulator or the glove on. So you just have a control. This is Josh writing his name again with just the muscle stimulator on and no glove. As you can see, it's a big difference in the writing. A lot of shaking, a lot of dots. And next is Joshua writing his name again with the glove running at full speed. Keeping in mind that we focus more on the wrist shaking rather than the fingers, so there is a little bit of shaking in the fingers, but overall you could actually see that the writing actually becomes better with the glove on. And finally you'll be able to actually see all of them close up to actually see the difference. So for us, this was a successful project. Now I'm going to hand it over to Alex for the closing remarks.
I'd like to thank everyone for spending the time to come here today to these presentations. And I'd like to remind everyone that Parkinson's disease and essential tremor are real problems and the people have to live with.